Good afternoon, everybody. All right, we're approaching the end of the course now. We've only a couple of more lectures of content to get through. So the guest lecture from Arab on Monday, and then next week we'll have one more guest lecture as well from Engineering Boston Scientific on some of the models that they use. And then in terms of content, sorry, I can't get this one to work. We're going to cover a bit of meshing and OpenFOAM, and then high performance computing will be the last piece of content we're going to cover that the last lab is on as well. And I think this week, it's near the end of this week, is when your assignment due, I think. No? Yes, I think it is. Very good. And then I guess most of you have received your provisional grades for the weekly assignments. If you see a mistake or anything, just ping me an email just to check, just because sometimes when we're adding things up, we make mistakes, that's fine. And then whenever you submit the last week 12 one, probably within a week of that, we'll grade those ones as well. So you'll have those ones before, and hopefully even the grades of the assignments before you do the exam as well. Any other questions or comments? Okay, in this lecture, I'm going to talk a little bit about mesh generation in the OpenFOAM software. And then depending on how we go for time, maybe I'll get a little bit onto showing the effect of some equations in OpenFOAM as well. So this overlaps a little bit with lectures earlier in the course where we talked about practical applications of meshing, or practical tips for meshing. But you'll see it from an OpenFOAM perspective. So within OpenFOAM, like other softwares, there's many tools, but as you've seen, OpenFOAM is a little bit different how it's designed, because it's a selection of command line utilities. It's not all a graphic interface with options. But broadly speaking, we can split the different mesh-related utilities in OpenFOAM into generation and conversion. So generation just means make a mesh based on some input file. Some input file that gives a CAD or says what your geometry looks like and how you want to define that, and conversion. So if you make a mesh in any common meshing format, you can get it into OpenFOAM. And even if you can't get it into one of the available formats, there's almost always a way to get it into one of these formats. So there's something called Mesh.io, a Python tool out there that converts between loads of different meshing formats. So if you have a mesh, you can almost always get it into OpenFOAM. But there are some built-in tools. They're normally fairly descriptive. So Fluent Mesh to Foam is a utility that converts a Fluent Mesh to an OpenFOAM mesh. But there's other ones as well. Gmesh to Foam. Gmesh is an open source meshing software. But then in terms of generation, the two utilities we cover in the tutorials or in the labs, weekly labs, are block mesh and snappy hex mesh. So block mesh is this simple structured mesh generator. So if your geometry can be described by simple shapes or collections of simple shapes, block mesh will work. And it's very simple to use and very quick. And then snappy hex mesh is a more general measure for complex CAD software. So I'll talk a little bit about both of those, but there are other tools out there that we're not covered, like CF Mesh is very similar to Snappy Hex Mesh, except it's made by a different company. And then there's some other mesh generators as well. So I'll spend a little bit of time talking about the block mesh utility, and maybe I'll flick over to the terminal and just give some examples just to walk through it as well. But broadly speaking, block mesh is just a very simple mesh generator tool that lets you generate the block meshes from a block skeleton approach. So it's only for structured hexahedral meshes, or in 2D would be quadrilateral, so like squares or cubes. And the way it works is your input file is you describe your geometry, the key coordinates of your geometry, and then you have to, before you write that utility or that tick, you have to split your geometry into this block skeleton. So this is when we talked about structured meshing before. To use structured meshing, you have to partition your geometry into 4-sided shapes in 2D or 6-sided shapes in 3D. So you have to do that for block mesh, and then you define the coordinates of those. So when you run block mesh, the command line utility reads a dict called block mesh dict. So this is pretty common in OpenFOAM. If you have a utility and it requires inputs, the inputs will be in a file that's the name of the utility with dict at the end. So block mesh dict, snappy hex mesh dict, extrude mesh dict, etc. And also, you may have noticed if you've done the first OpenFOAM tutorial that even for 2D problems, OpenFOAM treats them as a special case of 3D. So in OpenFOAM, if you do a 2D problem or a 1D problem, it is just a 3D mesh where it ignores, or not ignores, it has a special boundary condition in the out of plane direction. So if you do a 2D problem in OpenFOAM, they really will make the 3D mesh that's one cell thick, and then they have a special boundary condition on front and back, which says they call it empty, which means don't solve in that direction. The reason they did that is in Fluent, at least it was the case, I think it still is the case, that Fluent has separate 2D solver and 3D solver. So when you solve in 2D, it's different code than in 3D. So there may have been different teams that developed that. So you may not necessarily get a consistent answer. I'm not saying there are any inconsistencies, but it just means there's essentially two code bases. You have to have, if you implement Upwind, you have to check it works in 2D and you have to check it works in 3D. They're two different implementations. Whereas in OpenFOAM, they said, let's just treat everything as 3D and 2D is a special case. So if it works in 3D, it'll work in 2D. It's a special case. That's the approach they adopted. So what information is required to fully define a mesh? So I think this might be easier if I just flick to the terminal and do a more kind of hands-on approach, and then I can refer back to this on YouTube. This connection is not great. Come on. All right. Let me hide this thing. All right. It's okay, you can see that. Okay, so let me see. Okay, I have a bunch of cases here. Let me just delete this cavity case. So in OpenFOAM, if you have OpenFOAM loaded, so in this case, I have OpenFOAM 9 loaded. As we mentioned before, OpenFOAM comes with a bunch of tutorial cases already set up. So if you type tut, T-U-T, and press enter, it brings you to those tutorials. And then if you go ls, you can browse through them yourself. So they're broken down by different areas and you can go into each one. So one that I'm going to use, because it's often the starting tutorial in OpenFOAM, is if you go into incompressible and ICOFOAM. So ICOFOAM, I guess the word ICO came from incompressible or incompressible Navier-Stokes, I think is where they came from. And this cavity tutorial. So there's a few variants of cavity. So here's one variant. So it looks like I actually already ran this case. So what I'm going to do is, actually, I probably shouldn't be running it here in case I break my installation, but I will type run. So run is normally, you can run your models from anywhere, but OpenFOAM, they normally suggest you put your model in a run directory. So just keep them all in one place. So if you type run, it's just a shortcut that brings you to this run directory. So I'm going to copy cp-r because it's a folder. And then there's a bunch of what are called environment variables set up when you load OpenFOAM. So environment variables are normally capital letters. And for example, foam tutorials is one. And when you type $, it means the value of that. So there's a bunch of these environment variables set up. So if I go echo foam tutorials, you can see that that is a variable that's already set up to point to a particular directory. There's one called foam solvers. If I press foam and press tab twice, it just shows me all the different ones that are available. So I'm going to go cp-r $foam tutorials. And then I'll go / incompressible. And if I press tab, it actually auto completes it anyway. ICOFOAM, cavity, cavity. And I'm going to copy that to my current directory, which is run. Okay, so here's my cavity. You can see if I have some other cases there as well. So let me just delete the results, the previous results. So if I just go 0. I could go 0.1, 0.2, etc. But if I just go 0. Star, it'll star is a wildcard. And I'll delete that case.foam as well. So normally it'll just look like this, but I obviously ran this before. So if I go 3, you'll see the setup of this directory. So it's normal OpenFOAM case has a 0 directory with its the fields you're solving for, so lasting pressure here. So initial and boundary conditions are given inside there. You have a constant folder which contains the mesh. This already has the mesh because I must have ran block mesh already, but that's fine. Then transport properties will be interior properties. So normally the mesh interior properties are given here, and then system will be inputs for various utilities. So for example, here's the block mesh dict, which we're going to look at. The control dict defines the time step sizes, the end time, how often the results are written, whether things are written in ASCII or binary, or they're compressed or not compressed. And then the FE schemes and FE solutions are to do with the discretization and solution tolerances. So if I have a quick look at each of those, I know we briefly looked at them last night, maybe. This is the control dict. So all the OpenFOAM dicts tend to start with just the header. That's just comments. That's not read by anything. It's just to show which version of OpenFOAM this file came from. We also start with this kind of foam file header as well. And then normally they're set up in terms of key value. So key is, in this case, is like the word application, and its value is IcoFoam. So in the OpenFOAM code, it looks in a dict for a particular key and then finds the value of it. So if we go to, say, delta t, that's the time step. So that's set to 0.05. The end time is set to 0.5. So you can see it's doing 100 time steps. And then the right interval, that's how often the results are written, is every 20 time steps. So it solves every 5 milliseconds, but it's writing results every 20. And then there's some other settings here as well. Yeah. Okay, and then if I open FP schemes, we briefly had a look at this, but this is like in Fluent where you're switching between the time discretization, where there's first or second order racket, and the same with the gradient and divergent schemes. So this is like upwind or second order schemes or whatever. So this is, there's a direct mapping with what Fluent might do as well. One thing you might ask is, well, in Fluent, there's a drop down. I can see Euler as an option, but I can also see like second order Euler as an option. How do I know what the options in OpenFOAM are? So normally they typically call like the banana method. So you just type in something which is not a scheme and then run the solver, and then it'll say banana is not a scheme. Here are the schemes. So for example, if I write banana here and I write IcoFoam, it'll say unknown DTT scheme banana. There are 8 valid schemes here there. So this is, I know it might seem like a kind of a silly approach, but you don't have to type banana. You can just type anything that's not a scheme, but you can see the other options available. Let me switch that back to Euler. So there's those schemes. And then last one before I look at block mesh, take this FP solution. So this is when it's solving the P equations or the U equations. This is the actual linear solver. It's using a conjugate gradient solver and the tolerances. So these, you can set these in Fluent as well, but they're, I guess often you might not change some of these. Okay, so the one we actually came to look at, the block mesh dict. So just to reiterate, the block mesh dict is not the mesh. The block mesh dict is just an input for a utility called block mesh, which generates a mesh. So you don't have to generate the mesh with block mesh. It's just, that's the approach used in this case. Okay, so it's a pretty simple format. It starts with just a global scaling. So sometimes you might want to generate your geometry in millimeters. It's just more convenient to give coordinates in millimeters. So you can just give a global scaling, multiply everything by 0.001 here. So in this case, they've given everything in centimeters. So this convert to meters, that all the coordinates that are given after that will be multiplied by that. So these coordinates that are 1 will actually end up being 0.1 in the final image. So we want everything to be in meters normally. Okay, so how does this work? So in this case, it's a mesh, and let me just open up the mesh in PowerView so we can have a look at it. So in this case, it's a very simple geometry. It is just a cube geometry, essentially, or a square. So I press apply. I turn on the mesh. So it's a 2D test case. That's just a square. So a square is obviously very easy mesh or geometry to create a structured mesh of, because you just need one block from a block skeleton, and you just say how many cells in the X, how many cells in the Y, and then you're done. you drag and rotate it, you'll see that even though it's 2D, OpenFOAM does a 2D mesh as just a special case of 3D with one cell thick. So to define this geometry, we just have to give the 8 coordinates of this block. So if we had some other geometry that we needed multiple blocks, we would just give the corners of those blocks. So in this case, we'll see we'll have a coordinate down here in the bottom corner, which is the origin, and then we'll define the points in one plane and then the points in the second plane. The thickness in the third direction doesn't matter for 2D. It's just for visualization purposes, you might want to keep just something similar to the other dimensions. So if we look at the coordinates here, you'll see that 0, 0, then it moves in the x direction, then in the y direction, then to the top y. So what it's doing here is on the back plane, it's going, let me see if I turn on outline. So it's going 0, 0, then moving the x direction, 1, 0, then 1, 1, 0, 1. So that's these back ones. And then the front plane is just the same things again, except they've just made it 0.1 in the z direction. So that's all they're doing there. So the order of these vertices doesn't matter. When you're defining those in block mesh, we can switch these around and it doesn't directly matter, but it indirectly matters. So you can add a load of points here. So I could add another point here, like 100, 100, 100, and it shouldn't make a difference. So you don't have to use all those points in the rest of the mesh. So that didn't affect my mesh in any way. So if I refresh my mesh, adding a vertex there doesn't do anything. It's where they actually do something is in these blocks. So these blocks here, and I can split it across multiple lines. That's still allowed. So even though this is not C++ code, this is just an input file. They broadly follow C++ syntax. So if you want to put a comment, you can go, this is a comment. And C++, the code will naturally read across multiple lines until it gets to normally a semicolon to end the statement. So the way it works is you'll always start with this word hex. In fact, they probably could get rid of that because it's always a hex. And the other cases they were considering aren't, I think, properly implemented. And then the way it works is you give the 8 corners or the 8 vertices of that block. So these are the vertices back here. So if you look at this, it's gone 0, 1, 2, 3, 4, 5, 6, 7. So 0 here refers to, let me move this onto new lines so we can see stuff. So this 0 refers to the 0th vertex in the list above. So the 0th vertex is just the first one essentially. So this is vertex 0, 1, 2, 3, etc. 4, 5, 6, 7. And then this will be 0.8 I added or any ones after that. So even though the order doesn't matter here, if you change the order of these, your block definition may have to change to still be appropriate. So if you see the way this is done here, they're just listing the 8 vertices of the block. So you can see 0, 1, 2, 3, 4, 5, 6, 7. So to define the block, obviously you need the 8 coordinates. That makes sense. And you might think that the order doesn't matter, but that's not true because if you give 8 coordinates, I'm not sure how many ways you can connect 8 coordinates. I'm sure that's actually probably a known thing. But there's more than one way you can connect 8 points to make a block. So for example, if I just took those top 4 points and then the vertical lines, if I just flick them to not connect to the point straight above, but the one around by an angle, that's one way to do it unless you keep doing that around, and you can do that from every perspective. So there probably is a known solution to how many ways you can connect them. So you have to give more information than just the 8 vertices. So the order of these 8 vertices matter. So the way you define it is you pick a plane of your block, any plane, and you give the 4 vertices of that plane going in a clockwise direction, but a clockwise direction from looking inside the block. So let me repeat that. So if the 4 points that are being defined here, so if we go 0, 1, 2, 3, that would be this point, this point, this point, this point. Okay. So if the way I do it is the right hand rule, so if I get my right hand and my fingers are the direction going around, then my thumb should be pointing into the block. So if I put imagine that back plane, if I put my thumb on that back plane, my fingers, the points are going this, that goes around that way, my thumb is pointing into the block. So if I went in the opposite direction, that would be defining it the inside out basically. So the way you do it for a block mesh is you will define one plane with the right hand rule. Sorry, that's anti-clockwise. Anti-clockwise with your thumb pointing in. And then the second plane, you should start from the first point on that plane that connects to the first point that you started on previously, and then go in the same direction. But it doesn't matter. It doesn't matter which plane you start at. That's just one way they've done it here. So for example, if we were to start on the bottom here, I would go this one, this one, this one, this one. So that's anti-clockwise, my thumb pointing into the block. And then I would go straight up to start at the same equivalent point above. So this. So just to show you how you could change it. So we have 0, 1, 2, 3, and then we're going 4, 5, 6, 7. But instead of 4, if we started at 5 and went 5, 6, 7, 4, then it would connect them differently. That would be a valid block, but it would just connect them differently. So let's say get rid of 4 and put that over there. And then I write from block mesh. Oh, it doesn't like all the boundaries at the bottom. So let me just for demonstration purposes, I'll get rid of all of these. Okay. So if I refresh that, then, oh, did that complain? Oh, might be complaining. Okay, maybe that's probably a bad example to give them. And so let me go back up here. Here. Okay, so there are multiple ways you could define it. So I could define the mesh using any of these planes. So if I were to go at the bottom and I could probably figure out the numbers here to go around this way and that way, and then you could check that would work as well. So there's more than one way to define a valid block. So once you've defined that block, then the next thing you have to do, these three numbers, define the number of cells in each local direction of the block. So 20, 20, and 1, if we turn back on our mesh. Oh, okay, you can see the mesh actually it has the same bounding box, but you can see it's all twisted because of the way that I twisted those points around. If I go back to the way it was. We can see the mesh like that. So you might think that 20 is how many cells in the X direction, 20 in the Y, and 1 in the Z. So that is the case here, but technically what these directions refer to is the local direction. So 20 in the local first direction, 20 in the local second direction, and 1 in the third direction. And the local first direction is defined by the direction from the first point to the second point, so 0 to 1 here. So if we go back this one, oh, not wireframe. So the first coordinate to the second coordinate, that defines the local X direction, and then the second to the third defines the local Y, and then Z is the third direction. So as you expect, if I set that to 40 on block mesh, sorry, if I make this disappear, if I have to press escape and then it appears again. So, 40. And if I go snappy hex mesh, all right. So you can see now I have 40 in the local X direction. And then if I set this to say 200 in the Y direction, you know, block mesh, it's a little bit slower this time. Refresh, you can see, okay, we have 200 in that direction. Okay, so this is a very simple mesh, but the block mesh can be used to create complex geometry. Some, for example, like turbos or pumps can be described by simple geometry, like with curves. And if you have a mesh set up with block mesh, it's very easy because it's parameterized. You can very easily and very quickly generate a new mesh. So if it is possible to use something as simple as block mesh, it makes your life much easier. Okay, so let's step back to 20. And then the last thing here is the simple grading. I don't know if that's something you have to look at in the tutorial. I can't remember. but this gives the ratio of the first cell in the local X direction to the last cell. So if I set that to 10, the first one, run block mesh. Let me just start warnings annoying me. Get rid of that. Okay, so refresh that. Okay, so you can see in the local extraction, the ratio, I think it's the ratio of actually the last cell to the first cell is 10 in this case. So that allows grading in a particular direction. Or, for example, you were to go 0.1 in the Y direction. You can see in the Y direction, the ratio of the last one is 0.1 to the first one. So like if it's in the wrong direction. So you can use that to grade in a particular direction. And also, I'm not showing it, I won't show it here, but that's simple grading, but there is an option to do two other types of grading. One I think is called edge grading. Where is it? Yeah, edge grading. So in that case, all 12 edges you can give different grading factors on. Or you can do something called multi-grading of a block. So you can have the first 20% use a certain grading scheme, like uniform, the next, say in this case, 60% use a different grading, and then the last 10% use a different one. So for example, if you had a channel with flow, you might have a refine the mesh near the wall, like grade it to the wall to get a certain Y plus, but then in the central region you have uniform cells, and then near the top wall you might have a different grading towards the wall as well. All right, so then let me just reset those. And then the last couple of parts is by default, it will assume that the edges are straight lines, say connecting two coordinates, they're straight lines. But if you want, you can make those be various different settings. I don't know actually if the banana trick will work here, so let me see if it will. Yes, it does. Okay, so the block edge type, it doesn't know banana, but you can have an arc, a line, a polyline, project curve, spline, B-spline, so a few different options. So for example, a simple one is an arc. So let's say between point 0 and point 0 is here. So vertex 0 and vertex 1, we want to have an arc there. So the way you define it is you go arc between 0 and 1. And then how do you uniquely define an arc? Well, there's a few different ways. You can find a radius, or you can just define a coordinate. So if we give a coordinate on the arc, that would uniquely define it. It's the 3 points. So I think this point is 0, this is 1. And then, so this will be 0. Let's pick a midpoint. So 0.5, let me just check. That definitely was it. Yeah, 0 and 1. So 0.5 in the X, and 0 in the Z. So then we just have to pick a Y coordinate. So let's say if I make it 0.1, that would make an arc that's a little bit positive, like a little curve of that. So if I run the mesh with that, and then I go back here, you can see that it has made an arc on that. So that's a valid 3D mesh, but it's obviously invalid for 2D. So for 2D, it has to be the same in front and back. So if that was 2D, then you'll go, all right, let me just copy that arc. And then the front point, if it's 0, 1, 2, 3, then it'll be 4, 5 is the front. So you go 4, 5. And then it'll be the exact same thing, except I think was it 0.1 in the Z direction. Yep. So then you can have your arc that looks like that. And then you can do that for any of those edges. So you can do a spline as well, or I can't remember, polyline. I think you can give a list of coordinates and it'll project to it. And there might be some other more advanced features where you can project to a CAD surface or something like that. So you can imagine if you have an atmospheric flow and you want to project onto a landscape, you could project onto that. So. Okay, and then the last thing to define is the boundary patches. So you saw there, if I just commented out everything inside boundary, that will make a valid mesh, but it just notices that there's all the faces on the outside of the mesh are not put into any patch. It calls them patch, the boundary, like regions of the boundary. So it adds them all to a patch called default faces. So that means if I want to play a boundary condition, like an inlet, an outlet, a wall, it won't be able to select those. So it's not like an abacus where you can just open it up and select a bunch of nodes. You actually have to have them specified. So that's maybe a bit inconvenient, but that's the way it works at the moment. But there are tools to select them later. But normally in your mesh, you will create them in a certain way. So let's look at the different patch boundaries. So in this case, so we have 6 faces of this block, 6 outward faces, boundary faces. So we're going to define this as a moving wall for this cavity test case. So it's kind of like a conveyor belt is rubbing along the fluid in the constant velocity in the x direction. Then we'll have a, excuse me, a no-slip wall here, no-slip wall there, no-slip wall there. And then front and back will be empty. You can, for empty patches, if you just don't define them, it'll automatically set them to empty. So you don't actually have to define them, you can leave them out. So then the last question is to understand block meshes, how do you define these? So you can already see there's this particular convention, you just give a name. So moving wall, that can be called anything. Type wall. There are other types. The other types are, we can do the banana trick to find out the other types, but essentially symmetry is a type. Inlets and outlets are called just patch. So wall is, it's when you, if you possibly will use wall functions, then wall lets it know where they should be applied. So, and that's the only reason to call it wall. You don't have to use wall functions, but it's just, it has to be a wall to use a wall function. So how you define these patches are, you give the 4 vertices of the block. So in this case, this moving wall. So just to remind you, we have vertex 0, 1, 2, 3. So 2, 3 is the top there. And then it goes 4, 5, 6, 7. So 6, 7. So 2, 3, and 6, 7. So 2, 3 at the back, 2, 3, and then 6, 7. They're the vertices. So we want to define that that quadrilateral region as one patch. So we need 4 vertices. And once again, it's not uniquely defined by 4 vertices. You have to give them in an order. And there's a convention about the order. So when we do the right-hand rule again, this time our thumb has to be pointing out for the boundary. Okay, so keep you on your toes for the block, that means, and for the boundary wall, have to be out. So if we go here, we have, what did I say was 2, 3, 6, 7. So if I started 7, it'd be 7, 6, 2, 3. So right-hand rule with my thumb pointing out. So I could start 7, 6, 2, 3, or I could go 6, 2, 3, 7, or 2, 3, 7, 6. And they're all valid definitions. So you can see they've gone 3, 7, 6, 2. So 3, 7 is 2, 3. So 3, 7, 6, 2. So they started there and went around that way. So I can check that's a valid mesh, fine. But if I also copy that and I went, instead of 3, 7, I just start over here, go 6, 2, 3, and go 6, 2, 3, 7. So that's just starting with a different coordinate. So that's also equally valid. And that'll give the exact same definition. So that's how you define the patch. And if in the case of the fixed walls, we actually have 3 boundaries. So 1, 2, 3, or not 3 boundaries, 3 faces of blocks. So it's this face, this one, and this one. So if you pick that one, we had 0 is that's 1, and then was that 7, and that was 3. So you would have to go right-hand rule again with your thumb pointing out, the same for the bottom boundary, or the same for the side boundary. So that's those fixed walls, and then the front and back, you can see 0, 3, 2, 1, and 4, 5, 6 as well. So that's that, and then okay, you can run the solver then and see what effect it has. If I run it in this case, go blah blah blah. Let's look at the velocity. Okay, so this is pretty similar to the default case. This bottom boundary changing the shape of that didn't change very much, and this is the first tutorial or second tutorial that you have to run anyway. So this is not very exciting. This is just you get a rotation of fluid, but it's just a common CFD benchmark. Okay, let me see, is there anything more on that dimension? No, unless there's any questions on that. Right. Get a review. So these slides, I'll skip through them now, but this is saying the same thing that I just said there, except probably a little bit more dry, I suppose. Okay, so it's defined in planes. This is just for reference. And actually, this is fairly well described online anyway. So you probably will describe it, find it very well described on OpenFOAM.com and .org. And because it's described well online, ChatGPT probably understands it quite well also. So if you don't understand this, ChatGPT may do a better job explaining than I will, but feel free to ask me as well. Okay, so this defines all that stuff, and here's the other types of, there's other special types of entry conditions which we don't care about. But what I do want to cover before the end of this class is, the other type of meshing methods. So snappy hex mesh, I just want to briefly touch on. So this is a type of meshing called Cartesian meshing that we didn't really talk too much about when we went through practical meshing approaches, because their abacus didn't include this type of meshing approach. But it does appear in certain places. All right, so this is a lot of text just for reference, but I'll just go through the images instead. So the way a Cartesian meshing approach works, and sometimes it's called an octree meshing approach as well, is you start with your domain, and then you have a CAD geometry. Often the CAD is in a faceted format. A faceted, like an STL or 3D printing, is like, it describes the surface in terms of like little triangles or something. So not like an aegis or something like that. It's normally faceted. And what you do is you make a background grid over the CAD where you were interested in looking at the flow, so this flow around the car. And snappy hex mesh are these Cartesian-based meshing approaches. Normally what they do is, the first step is they determine where the CAD surface overlaps the background grid. And then, depending on what the user tells them to do, they may refine that. So they might split that. So you'll see that you have what in finite element they would call a hanging node. It looks like a square with a little squares. But actually for finite volume, it doesn't care about that. That's not an issue, because this shape here is actually no longer a square, it's a pentagon, because this is one face, this is another face, this is one, this one. So this shape now has 5 faces, 1, 2, 3, 4, 5. So if it's all polygons or polyhedra, then it's okay to have a mesh like this. So it refines it. Then the second step is it removes the cells where you're not interested in the flow. So that could be flow. We're interested in flow around the car here, but you could also have a piping system, and then you keep the cells inside, get the cells out, get rid of the cells outside for internal flow. And then the next step is this, where snappy comes from, the name. Snappy snaps or projects the surface, which is castellated like a castle or like a Lego. So it projects those coordinates back to the surface, and then maybe smooths their background mesh. Get something like this. And then you could run your analysis on that already. But let me see. I skipped over 2 steps of the chart I haven't shown here. You'll notice here that they've actually refined a grid here. So where the wake, they expected the wake, you can also put a refinement box. And then one step I'm not showing, which is important actually, is the worst cells are right at the surface. So if you're interested in the drag on the car, this will be a terrible mesh, because you have like really terrible cells. So the wall shear stress calculation will be very poor. You can't control your Y plus. So they normally will grow layers, boundary layer cells as an extra step, which is often the slowest part of snappy hex mesh. So it pushes this mesh back to try to get very nice orthogonal cells around the boundary of the car. So you can try a test case. Let me check it here. I won't do it now. So this test case called motorbike is in OpenFOAM. In all the versions it has it. So this little pad guy, you can run this case, and it only takes like, I don't know, it took maybe 10 minutes on my laptop or something. So it's like a really, let's say, industrial case that you can try with SimpleFOAM solving. But to run it, you go to run, copy foam tutorials incompressible SimpleFOAM motorbike, copy to your current directory, CD into it, and then just run the all run script. So // will execute the all run script. If we look at the all run script, what's it doing? First thing, it's just copying. The little motorbike man is actually stored somewhere in OpenFOAM, so it copies it into the case in the first place. Then it runs block mesh to generate the background grid, because snappy hex mesh doesn't actually generate the background grid. And then snappy hex mesh then will cut the motorbike man out of it and refine the grid all around it. And then it will run this get application runs SimpleFOAM in parallel, and it runs potential foam as well to initialize the velocity field. So this would be like very representative of, let's say, an industrial workflow for OpenFOAM. So you can try this case yourself. So you'll see that the final OpenFOAM tutorial, excluding the HPC one, so the one I guess this week, is a matchstick box car flow over. So it's a very similar workflow to this. So it's a relatively powerful mesh, I'd say. So you can check that out. Yeah, I might just come back to this video. This is it's a cool video, but I just want to mention one other thing, just as an example. You can find this in IcoFoam. You saw there was this elbow case. So elbow case includes a Fluent mesh generated in Fluent. And you'll see that you can just run it by going Fluent mesh to foam. That generates the mesh. There's no block mesh stick. And then you run IcoFoam. And then you'll get a flow. In this case, you have a big inlet with slow velocity and a small inlet with a high velocity, and then an outlet over here. So you can get mixing of it. So I'll just end by looking at this. Oh, hopefully this is not super loud. Sometimes it blows the head off of it. Okay, well, sounds not working. There's not much sound to it anyway. It's just this is an interesting case, this drive air model. So drive air was a project. I think it was some of the automotive companies came together to try properly validate benchmark safety tools. So they all agreed on a particular setup of cars, and then they ran very detailed wind tunnel tests on them. So in this case, TUM. So TUM is Munich University. And they ran a test case, and then many people will analyze this. This drive air model is like a well-known benchmark. So you can see that they're measuring lots of things. But if you check, people be using RAN. So there's various different meshes you can imagine. They're getting into the millions of cells for them. But let me just see. I think there's some interesting things to look at. People in this video, they're looking at different meshing types. So I don't know how they generate this, but they're nice boundary layer structured mesh, and then they have tetrahedral mesh far away. I guess this might be Fluent. Fluent can do this, but Fluent also has polyhedral cells far away. So it just gives you some idea of the challenges involved in setting up these cells. So you can see their first height is 0.8 of a mil, so less than a mil. And then challenges for the mesher, getting layers over all your geometry is almost impossible. So in between the tires and everything, there's just parts where you just won't be able to grow layers properly because the geometry is just too messy and complex. Well, I think they're trying to show off here that this is like very good coverage of boundary layers. But you can see they're actually modeling the full inside of the wind tunnel, and you can see the fine areas in the wake. And let me just show you they also looked at this. It would be like a snappy hex mesh style approach. I don't know if this is snappy hex mesh or a alternative measure, but look, you can see the cell counts that they're looking at, the order of tens of millions. But I think some of the results are interesting to look at. So they would have, this group would have compared RAN's approaches with DES or LES style approaches and taken the average to try to understand how accurate some of these models are. So this is a RAN's approach, and then IDES is, imagine it's like a step towards LES. So DES is like a slightly cheaper version than of LES. So you can see this is a truly transient simulation, and then if you take the average of that in time, RANs should give you that, but it's an approximation. That's it. So they're able to use this to like as a benchmark of CFD tools. Check how good they are at different types of predictions. Let me just see if there's any other things. Yeah, it's interesting to see some of the results. So in terms of detachments, and this is a way to benchmark turbulence models as well. So you can compare different RANS models and find which ones for these applications might be better at capturing the true dynamics system. Okay, I'll stop there, and there's going to be no lecture on Wednesday, so I'll put an announcement on that. So you have a lab on Thursday, and then there'll be 2 lectures next week. Thanks so much.